Hello everyone, I'm Hiroki Yamada. Today I'm talking about ScalarDL, which is scalable and practical Byzantine fault detection for transitional database systems. This is a joint work with Jun Namato. We are from a startup called Scalar based in Tokyo, Japan. We are living in a data-driven or data-centric world where lots of things are decided based on data. So we want a data to be reliable and trustful. And data is usually stored in a database system, so we want a database system to be reliable and trustful as well. One of the keys to realize it is to deal with the Byzantine faults in a database system. Byzantine faults are arbitrary faults, including not only software errors, but also data tampering, malicious attacks, and internal attacks. Our goal is to create a database system that deals with the Byzantine faults in a practical and scalable way. The basic principle of dealing with Byzantine faults is finding discrepancies between replicas. There are essentially two ways of dealing with Byzantine faults. One way is called Byzantine fault tolerance, BFT. BFT masks Byzantine faults as long as n is bigger than 3f, where n is the number of replicas and f is the number of faulty replicas. They have been several research work, and it's been progressing a lot due to the emergence of blockchain. The other way is called Byzantine fault detection, BFD. BFD detects Byzantine faults instead of masking them, but it detects it as long as n is bigger than f. Let's see if existing solutions are practical and scalable enough for creating a reliable database system. Let's first look at the BFT. In terms of security, BFT is ideal because it can mask Byzantine faults. So even if Byzantine fault occurs, we can proceed as if nothing wrong happens. But as a downside, it requires at least 4 separate administrative domains, ADs. Let's assume there are 4 replicas. In this case, we need the 4 separate administrators or organizations to take care of Byzantine faults, including malicious attacks. This is because malicious attacks are very likely to be dependent in an AD. But if there's a Byzantine fault in one of the replicas in an AD, then the other replicas in the same AD are also faulty. So we believe BFT might not fit well with enterprise database systems because enterprise database systems are mostly managed by a single AD or a few ADs. So next, let's look at the BFD. BFD can only detect Byzantine faults, which is less ideal in terms of security. However, BFD requires only 2 ADs to detect Byzantine faults, which is more practical from administrative and operational perspectives. So we believe BFD is a promising solution for database systems. And there are actually many use cases where only Byzantine fault detection or tamper evidence is required. However, the existing solutions are not designed for transaction database systems. In short, they cannot run non-conflicting transactions in parallel, so it's not scalable. So the challenge we're addressing here is how do we design a scalable BFD for a transaction database system that is deployed to a 2AD environment? Actually, there is no such work that focuses on the challenge. As we discussed, we believe BFD is not practical enough from an administrative perspective, whether or not it can handle database transactions concurrently. And BFD is not designed for database transactions. But it might be possible to apply the existing approaches to realize BFDDB. For example, we could make BFTDB into BFDDB. Or we could make BFDSMR into BFDDB. Let's see the 2 approaches in more detail to see if they are effective or valid. First, let's look at the BFTDB case. So BFTDB can run transactions concurrently while preserving correctness as long as n is bigger than 3f. Essentially, the way to making BFTDB into BFTDB is splitting up replicas into 2 ADs. Can we really do that? The short answer is no. This is because one Byzantine faulty replica will exceed the predefined threshold for correctness. its Byzantine faults are dependent on AD. Let's assume there are 4 replicas, and then 2 replicas in each AD. And let's say one replica is faulty. Then the other replica in the same AD is also very likely to be faulty. So 2 out of 4 replicas are faulty, which exceeds the predefined threshold. In this case, the system has to accept the fault, so data will be tampered. Let's look at the BFD SMR case. So BFD SMR is based on SMR, state machine replication. So it processes transactions or operations sequentially. Can we make BFD SMR run transactions concurrently? And the answer is yes, but only partially. We could apply some concurrency control in the primary side if we extend it. However, the witness side or secondary side has to execute transactions sequentially based on the hash chain execution log of the primary for correctness. So these 2 directions are either not possible as it is, or possible but not scalable. So we address a challenge with ScalarDL. ScalarDL is a scalable and practical BFD approach for transactional database systems. ScalarDL manages 2 types of servers and databases in separate ADs internally, which we call primary and secondary. ScalarDL is also database agnostic for additional practicality by depending only on common database operations. So it's not specific to a particular database implementation like a locking mechanism. The main challenge is executing non-conflicting transactions in parallel while guaranteeing correctness. The correctness here means it provides safety, meaning strict serializability, and liveness if there is no fault. It also provides safety if one AD is faulty. In this case, safety means correct clients can detect a Byzantine fault. Since it provides safety under a failure, it cannot provide liveness due to the FLP impossibility. The key idea of ScalarDL Byzantine fault detection protocol is making an agreement on the partial ordering of transactions in a decentralized and concurrent way. So either primary or secondary cannot self-officially order or commit transactions. The protocol is composed of 3 phases: ordering, commit, and validation, and it works as below. By the way, this protocol assumes one-shot request model, so a set of operations are packed into one request. Let's see at each phase in more detail. In the ordering phase, it orders transactions in a strict serializable manner with a variant of 2PL, two-phase locking. Since it does not know what records to lock, it simulates a transaction and identifies the read and write set of the transaction, and acquires locks based on it. Also, the lock acquisition is done by underlining databases serializable operations, which is common in many databases. The diagram shows the lock entry returned to a database. One key thing to mention is records are internally versioned, and the lock entry has the input dependencies of a transaction. The input dependencies are composed of a set of primary key version pair and then indicating the partial order of a transaction. It is used to verify the consistent ordering between a secondary and the primary. Then, if all the locks are properly taken, it goes to the next commit phase. You might wonder why it uses 2PL instead of recently often used multi-version concurrency control. The reason is, primary and secondary could derive inconsistent ordering without showing explicit order dependencies like a conflict graph, which is supposed to be not feasible. That's why we use 2PL. The next commit phase in the primary simply executes transactions in an arbitrary order. All the transactions that come to the commit phase have already been ordered in the ordering phase, so the primary doesn't have to carry the ordering. As the output of the execution, it creates proofs that indicate what records are actually read and written. The proofs also has input dependencies, which indicate the partial order of transactions and are used in the next validation phase. The final validation phase basically validates if the commit order in the primary is the same as the one the secondary expects. The secondary compares the proofs given from the primary with the log table entries, which also indicates the ordering information. And if this validation passes successfully, the secondary executes a transaction to derive the new states and results, and they are returned to the client for final validation. The client compares the proofs and results from both the primary and secondary to see if there is any discrepancy. If there is, then it alerts if there is a Byzantine fault. So, this is a basic way of detecting Byzantine fault in ScalarDL. However, there could be any crash faults during the processing, or there might be Byzantine clients that do not follow the protocol. We'll discuss them in the paper. We compared ScalarDL with the extended version of peer review, which we named peer review TX. Peer review TX executes non-conflicting transactions in parallel in the primary side, but executes transactions sequentially in the witness side. We did a comparison on PostgreSQL and in Cassandra. Workloads we tested are YCSV and TPCC. We ran experiments in AWS and used C5D4X large EC2 instances for database instances. We co-located ScalarDL servers and the peer review TX servers and database instances. This is the throughput results of PostgreSQL. X-axis is the number of client threads, and Y-axis is throughput. As you can see, ScalarDL outperforms peer review TX in most cases, and scaled well as the number of client threads increased. Instead, peer review TX's performance was saturated at around 4 threads. This is the results on Cassandra. We were able to observe similar results to the PostgreSQL ones. We also verified the database agnostic property of ScalarDL. We also verified the node scalability. We increased the number of Cassandra nodes in each AD and checked how it increased throughput. As you can see, the throughput scaled nearly linearly as the number of nodes increased. So we have presented ScalarDL, which is a scalable and practical BFD middleware for transactional database systems. The key contribution is the Byzantine fault detection protocol that executes non-conflicting transactions in parallel while guaranteeing correctness. ScalarDL achieved up to 10 times speedup and near-linear scalability. One important thing to mention is that ScalarDL is a real product, not a research prototype, even though it's a research paper. It's being used by our big enterprise customers in production. Please read the paper and check out our GitHub site. Thank you.